Hi, in this tutorial we are going to solve a question related to chiral centers, assigning R or S configuration to chiral centers, and deciding the relationship between different molecules as diastereomers, identical molecules, different molecules, or enantiomers. Okay, let's read the question. The question asks us, four molecules are given in the figure below. A, B, C, and D. For molecule A, indicate the chiral centers and assign R or S configuration to each chiral centers by ranking substituents. In order to solve this part, we have to redraw the molecule here. I have already drawn for you, and we have to indicate chiral centers. And here in this molecule we have two chiral centers, and let's indicate the chiral centers by red marker. So this carbon is a chiral center and this carbon is a chiral center because each carbons are having four different groups around them. So after that, let's go and rank the substituent around each chiral carbon. We know that we have to rank based on atomic number. Hydrogen should be always the last one, number 4, and bromine, if you look at the substituents, carbon, carbon, bromine, bromine has to be number 1 because it has the highest atomic number. And if you look at the other two substituent, which is carbon, carbon, which are carbon, carbon, carbons, but this carbon has 3 hydrogens, this carbon has bromine, hydrogen, carbon, so definitely this carbon should have higher priority than this carbon, so this has to be number 2 and this has to be number 3. Okay. After assigning priorities, we have to look at the number 4 least prior group. It is going behind the paper plane, so we can decide going from 1 to 3 clockwise R, or if we go 1, 2, 3 counterclockwise, that chiral center has to have an S configuration. So let's go from 1 to 2, 2 to 3, then from back to 3 to 1. This is a clockwise rotation. This has to have R configuration here. Let's write. Then let's prepare another template here. Then let's decide for the second carbon whether it has R or S configuration. Let's do the same because it has the same connections, same connectivity. So as the first one, we have bromine, hydrogen, carbon with 3 hydrogen, and carbon with a bunch of different groups. So hydrogen should have last priority, and bromine should have first priority, and carbon with bromine should be number 2, and carbon with 3 hydrogen should be number 3. Let's go again clockwise or counterclockwise from 1 to 2, 2 to 3, and 3 to 1. This rotation is counterclockwise, so this chiral center should have S configuration. Okay, we decided R or S configuration for both chiral centers. We can move to second option in this question. It says that using your results for molecule A, indicate R or S configuration for the chiral centers in molecules B, C, and let's say also D. Okay, let's write back to A, then it will be easy for us to decide for the other ones. The first chiral center in A has R configuration and the second one has S configuration. If we move to B, we can compare two chiral centers with the chiral centers A. Let's look at the first chiral centers is exactly the same chiral center with the same connections, with the same order, same places, so we can definitely say that this has R configuration. Let's look at the second chiral center. Second chiral center has opposite configuration with respect to the A's second chiral center. Why? Because we have methyl going behind the paper plane, but in this one it is coming out of the paper plane, so hydrogen and methyl exchange bromine at the same place. So we know that if we exchange two groups in a chiral molecule, the configuration should revert. So this chiral center should be R, because the first one in the first molecule, the second chiral center has S configuration. This one should have R configuration because of the exchange of two groups. Let's look at C, and we will compare again with A. Methyl and hydrogen are in the opposite places, so this should be the opposite of R here, which is S. And let's look at the second one. Second one is exactly the same as in A. H behind methyl front, H behind methyl front, so it has to be the same as in the A molecule. And let's do for the last molecule, D. Methyl behind methyl front, so it should be the opposite, so this has to be S. And then let's look at this one. Hydrogen behind, here hydrogen in the front, so it should be again the opposite of the second chiral, which should be here R. So we decided R or S configuration for each chiral centers in 4 molecules, and the last parts of the question says that indicate the relationship between AB, AC, BC, and let's say here also C and D. C and D. Okay, and let's write here AB. Let's look at A and B. A has RS configuration, B has RR configuration. So the first is the same, the second is different. As total, they are not reflection of each other, so they cannot be enantiomers, and we have to say that they are diastereomers, and I'm going to abbreviate as dia. Okay, let's go to second one. It says A and C. A has RS configuration, B has SS configuration. The same case, second carbons have the same configuration. The first, they have different configurations, so they cannot be enantiomers because all configuration have to switch or change. So this is also diastereomer. Let's look at B and C. B has RR configuration, C has SS configuration. So both configuration change, they are reflection of each other, so we have to say that they are enantiomer. Okay, then let's go to C and D. C has SS configuration, D has SR configuration. Again, one is changing, the other one is not changing. Let's say this is also diastereomers. One last option we can add here. How about A and D? A and D. Let's put A and D. Okay, A has RS configuration, D has SR configuration, both changing from R to S, and the second from S to R. We are tempted to say they are enantiomer, right? Because they are supposed to be mirror image of each other. But don't forget, you have to check sometimes if a molecule is meso or not. If a molecule is meso, its mirror image is not it's going to be it's enantiomer, but it's going to be identical. Let's look at here. What is the definition of a mesomolecule? The definition of a mesomolecule is that it should contain a symmetry plane. Let's look at here. If I draw here a plane like kind of a mirror, and if you have a symmetry plane which is bromine bromine, hydrogen hydrogen, metal metal, exactly at the same places across the mirror. So this molecule will be a symmetric molecule, and symmetric molecules are meso if they contain two chiral centers, and its reflection, which is going to be SR, RS, the reflection SR, basically it's not going to be its enantiomer, but it's identical. How can we prove this? We have to look at the molecular models. If we look at this molecular model, this is exactly the first molecule A, two hydrogens coming front and two metals going behind the paper plane, and this one is the opposite. Two metals are in the front and two hydrogens are in the back. So they are kind of like, if we rotate this molecule, and if we rotate this molecule this way, and kind of there is here, if you think of there is a mirror, they are mirror image of each other, and they are supposed to be enantiomers of each other. But for the mesomolecules, if you place the rotating, you can superpose them, and the definition of enantiomers, they are mirror image of each other, but they are not superposable, they are superimposable, the definition of enantiomers. Let's move one to the other one, and let's rotate it, and we can exactly place them on top of each other, you see. So basically they are superposable. If two molecules are superposable, they cannot be enantiomers. So let's go back to our screen, and we are going to say that A and D are not enantiomers, they are identical. So at the end we decided that AB, they are diastereomers, then AC, they are diastereomers, B and C, they are enantiomers. And why B and C they are enantiomers? Because they are reflection of mirror image of each other, and also they are not meso. B and C are meso. Why? Because they don't contain a symmetry plane. That's the difference between A and D. And then we decided C and D diastereomers, and A and D, they are identical, they are not enantiomers, because A and D, they are meso compounds. Thanks so much for listening.